Um, yeah, I guess we can get started in a bit. We'll wait for everyone to kind of just join in, and yeah, so we'll get started in like 2 3 minutes. Okay. Is anyone having difficulties seeing the presentation? Uh, okay. See if anyone joins. Give it maybe 1 or 2 more minutes. See if no one joins. Okay. Okay, guys. So yeah, I guess we can get started uh, with today's lesson. So today's lesson is going to be on the K-Nearest Neighbor model. Um, and this model is mainly used for classification. So yeah, that's what we're going to be doing. And this is our second lesson. If you missed the first lesson was on linear regression. So I think last time we kind of did like a more of a lecture base. This time to kind of get you guys more interested and engaged, we're going to use kind of a more interactive forum. So feel free to raise your hand or just type answers in chat. Yeah, so I'll ask some questions and then you guys can answer in chat and I'll explain the answers. So whenever I ask you to question, what I'll do two things, and this is what we used to do in high school actually for the online year. What we did was our teachers would ask us to load our answers. So you just type your answers into the chat, and then when I say enter, you enter your answers in the chat. That way, everyone has an equal chance of reading the answer properly or reading the question properly or not being influenced by anyone else's answer. So again, please participate. It's for you. It'll help you learn more and learn faster. So yeah, I guess we'll get started now with the actual presentation. Okay. So the class structure for this class, we're going to do around 30 minutes of a lecture slash instruction slash our interactive session, 30 minutes of coding. We might fall short. So if I'm running short on time, I can always give you guys the Google Colab link and you guys can do it for homework. So again, please participate in chat and try to do the activities to the best of your ability. Okay. So I know we didn't really cover this last time. We dived straight into linear regression, but what is artificial intelligence? So artificial intelligence is the development of using a computer system that is able to perform tasks that a normal human would using a normal level of human intelligence. So currently we are at something called narrow AI. And there are three main stages for artificial intelligence. The first being narrow AI, the second being general AI, and the third being super AI. So narrow AI is more kind of when, like, say you have a machine that can only play chess, which we have, or a machine that can only determine if an image is a cat or a dog, so classification. So those machines are only really good at doing one thing, and that is performing a certain task. So that would be called narrow AI, and that's where the kind of machine learning and artificial intelligence field is currently. Next is general AI, and this is where people predict we would be if we keep our current pace up within 25 years, or even or 30 to 25 years, depending on various experts, if you ask them. So general AI is doing something that a human would do, but for everything. From you would have an artificial intelligence that could drive a car, that could kind of uh, classify between dogs and cats, that could paint a house, anything that a human could do, we would consider, and it could do all the various activities, we would consider general AI. And then super AI, the way I like to think about super AI is if you guys have seen the Iron Man movies and you've seen Jarvis, Jarvis is kind of like a super AI. The fact that he can do things that normal humans can't do. He can connect to satellites, destroy missiles on command, and release missiles on command. And in some ways, he's smarter than a superhuman, or smarter than a human, especially if you see like when Vision and stuff comes. So I'm a very big Marvel fan. So, but if you didn't get that reference, basically think about it as a really smart artificial intelligence that's smarter than humans. Um, Maybe if you've seen Terminator, but not exactly Terminator. Okay, so there are a few common artificial intelligence misconceptions. The first one is that the machine is learning. So again, the machine never learns by itself. It's always at the end of the day, there's always a human behind the screen, changing the parameters, hyper tuning, which means you're telling it how much to learn, how fast to learn, when to classify, when to do regression. So a lot of it at this point is still based on the human kind of interaction of it. Okay, and then the idea that super intelligent machines will surpass humans, or kind of that super AI, that's a long way off. We're still at the very beginning stages of narrow AI, and kind of not even close to seeing glimpses of general AI. And then the fact that AI cannot be creative is also a very bad misconception. There are a lot of new types of artificial neural networks that can create art and can create music. These are called generative adversarial networks, if you've heard of variational autoencoders. These are just different types of artificial intelligences, specifically narrow AIs that are really good at kind of creating things and being creative, as we humans would call it. But they probably think it's just kind of mixing and matching sounds or colors or whatever is happening over there. Okay, so there are three main functions of AI. The first is classification, which we'll be going over today. The second is prediction, which is kind of like linear regression and regression in general, which we went over last class. And then third is generation, which is kind of thinking about that creativity of AI, like generating new data or generating art or generating music. Right? And then some subfields of AI include segmentation and optimization. So segmentation is just a really fancy word of kind of determining parts, I think is the best way to say it. So if you have say like if you have say something like a petri dish, and in the petri dish you have say 100 bacteria, and you want the artificial intelligence to determine where the bacteria are and say, okay, this pink blob is a bacteria, this green blob or this is also a bacteria or whatever. That's called segmentation. And optimization is just another fancy word of saying how to make things go faster, go smoother, go better. So you always try to optimize whatever you try to do. So you'll always hear in a lot of CS classes that you should always be optimizing your code. Okay, so now we're going to get to the kind of interactive session of this class. So for each of the ones, I'll tell you guys to load your answers and what type of what are the main three types of like AI do you think each of them would do? For example, I'll just do the first one for you. So for the first one, we can see there is an apple and an orange. So the most likely AI for this would be a classification AI, kind of classifying fruits between orange or apple. Okay, so for the second one, load your answers in. I'll give you guys like 30 seconds. And then when I say enter, please enter. So yeah, just look at the picture and yeah, we'll see what you guys type of AI do you guys think it is. Classification, prediction, or generation. Okay, you guys can now enter your answers into chat. Okay, we're getting prediction and prediction. Yeah, so Joshua and Daniel, you guys are both correct. It's prediction. So this is actually a picture of the stock market, and I believe the dark blue line is actually predicting what the stock market is going to be like. Okay, for the second one with all the faces, this is a bit of a tricky one. Take your guess. I'll give you guys 30 seconds to load your answers in. Okay, you guys can now enter your answers. Okay, so we get a facial recognition and classification, generation, and classification. So yeah, I think yeah, this was a little bit of a tricky one, but this one is called this is generation, because all of the images that you see here are not of real people. So if you say that you recognize one of them, I could probably tell you're lying. So yeah, all of these are fake people, and these are images generated by a artificial intelligence model. Okay. Any questions on that? Oh yeah, does this person does not exist at pub? Yeah, Daniel, that's exactly what this is. That's basically what this image is. Okay, go on to the third one. Again, I'll load your answers. What do you guys think it is? And in 30 seconds, I'll go to your. I'll tell you guys to enter. Okay, enter your answers in the chat. Classification, classification, generation. Um, we'll wait for any more. Okay. So Joshua, in this case, it is actually classification, but regarding the last one, you probably like it's a bit confusing, I know, if you don't have any prior context. But the reason this one is classification is because if you look really closely, what you'll see is you'll see like under say the letter or the number 4, you'll see a small 4 right next to a parentheses and a 4. This is actually a classification model that is classifying these handwritten digits. And this data set is called MNIST. So the number without the parentheses is a true number, and then the number within the parentheses is the number that the computer thinks the handwritten digit is. Okay, so I hope that helps. We can just I'll just do the last one for you guys. So as you probably can tell, the image on the left hand side for the last one is a classification one, since we're classifying between diseased and healthy individuals. And on the right-hand side, we can see that this is a lot like our linear regression that we did last time. So we can actually see the line of best fit. So that one would be a prediction. So moving on. Okay, moving on. So we didn't really talk about the training and testing process last time, but training is kind of making the general rules of the model, and then testing is kind of like trying out the rules. So you can always think about it as if you're creating a video game, you always want to make sure that you don't have any bugs, and that's kind of your training part. And then testing part is when you're kind of playing your video game to make sure that there aren't any bugs. Okay, so there are two types of key training. The first is called supervised learning, and the latter is called unsupervised learning. There's another section that's also called semi-supervised, but we won't really be getting into that this time. So the only difference between supervised learning and unsupervised learning is that the data for supervised learning is labeled, whereas the data for unsupervised learning is not labeled. So you can think of this as, say you were teaching your kid to read or a child to read. You'd always want the child to know the alphabet first, so they can recognize the letters, right? So if they know that an A is an A, when they read the book, they can like, okay, this is an A, this is a P, this is a P, this is an L, this is the E, so this spells apple, right? So that's the kind of idea between supervised learning, is that the data comes with a label. So when it's training with the label. In unsupervised learning, there is no label. So it's kind of giving like a child a book to read and they don't know anything. It's kind of giving like a toddler a book and expecting them to figure out how to read by themselves. Okay, now we'll kind of just get into some classification versus regression. So if you remember from last class, we did linear regression where we attempted to create a linear function. Remember, linear functions are of the form fx is equal to mx plus some constant. And we tried to use this linear function to model our data and predict future values given our given some independent variable or some future independent variable. So today's lesson will be more on classification. So classification distinguishes between certain groups, or you can also call them classes. That's the word classification. And there are really a lot of different types of ML classification algorithms currently. The main key ones are support vector machines, Bayesian classification, decision trees, random forests. So there's a lot of them, and they've been around for around 35 years. But today we'll be going over one of the first ones I learned, and one of the things I think is the most intuitive to grasp, which is called the KNearest Neighbor algorithm. So think about it. We'll just go over the KNearest neighbor algorithm today, and you can think about K as just being a certain parameter, which will make more sense as we go on. Okay, so KNearest neighbor algorithm is also called KNN, just because it's easier to say. Okay, so KNN is the most beginner-friendly classification algorithm. It's really intuitive to learn, and it can be used for both binary and multi-class classifications. So what a binary classification is you have two things you're trying to classify between, say, cats and dogs, apples and oranges. That would be binary classification. Okay. For multiple class classification, what do you guys think that means? Just put that answer in the chat. I'll give you guys maybe around 20, 30 seconds, and then I'll tell you when to answer. Right now, we're just kind of going over the KNN algorithm, and this is kind of like the first prerequisite to the KNN algorithm. Hopefully that explains it. Did you miss anything? Okay, also you can enter your answers in the chat. No? Oh, it's okay. Here, I'll answer it for you guys. So multiple class classification is just when you have multiple classes. Say you're trying to classify between an apple, a banana, or apple, banana, and orange, or between an apple, a banana, and a laptop, or more than 3 or 4 or 5 classes. So yeah, that's basically what multiple class classification is. And then the next question, which I hope you guys can all kind of formulate, I won't ask you guys to enter this in chat, but just think about how do you think you learn, and how do you learn to classify, and how do you think a toddler or an infant learns to distinguish between faces and not faces, to distinguish between apples and oranges, right? So just think about that and kind of grasp what do they do. So, and because that's kind of the basic intuition on how the KNN algorithm works. Okay, so I guess we can move on to the next slide. Just in your mind, just keep thinking about how does a child learn? How would they classify things? How do you think they would classify things? Okay, so a child usually classifies images or objects by recognizing certain common features of an object. So if I gave a child an apple, they're going to remember certain special features. They're going to remember how does the apple look like? What's its general shape? What's the general color? What are the general color patterns? Is it more red than yellows? Are apples ever blue? What's the size of an apple? Is it the size of a TV, or is it the size of a ping pong ball, or is it close to the size of an orange? Or what are the spatial relations? And what this means is, for like example, recognizing faces, How far apart are eyes usually, or how low do ears usually go? So stuff like that. So what we call this is called features, right? We call these features or attributes because there are certain features or certain attributes, size, color, shape, spatial relations, that the child tries to learn about and tries to use them to classify. So for example, if the object is a new object, the child would probably use the features it already knows about to try to classify what that object is. For example, if we show the child an image of an animal, he or she, what they'll do is they'll look at the image and be like, okay, this image has 4 legs. So I can say that it's more likely to be an animal than it is to say an orange or an apple. So what we see that the child is doing is it looks at the image and it sees what the closest resemblance to that image is in its list of given features or given parameters. And then it classifies it within that class. So this is kind of that vague idea between the KNN model, is that you look at the features and you see, okay, can I use these features to classify another model or to classify another data point? So that's the main big thing about the KNN algorithm, that you already have to have data that's already labeled, right? You have to know that, okay, these 10 points I consider as, say, an apple. These 10 points I consider as a orange. So I need to know those data points and I need to know their labels. So the first question I'm going to ask you guys is the KNN algorithm a supervised or unsupervised model? And then the second question is, how do you think you can measure these similarities between classes? So I'll give you 30 seconds to answer the first question, and then 30 seconds to answer the second question. Yeah, Vedant, do you have a question? Let me just put it in chat. Okay, yeah, no worries. Okay, you can enter your answers for the first question. Okay, we have one supervised. Any other? Any other? Okay, supervised, supervised. Anyone else? Okay, so you guys are correct. It is supervised, but the reason it's supervised is not because you can measure it. The reason it's supervised is because you know the priorly labeled data, right? So for the KNN model, you have to know like X amount of data, and you have to know what type of data it is, right? So I can't just give you. I have to give you like uh, pre data, in the sense that I'll give you, okay, I know 10 of these points are apples and 10 of these points are oranges. So when I give you a new point, or new data point, I can then look at the respective similarities and then say, is it an apple or is it an orange, right? Because I know it's labeled. And remember, that was the main thing about supervised and unsupervised learning, that supervised learning uses labels and unsupervised learning doesn't use labels. I hope that class kind of alleviates any errors or any doubts you might have had. Okay, we can go on to the next question, next part. Okay. Oh, the second question. I'll give you guys 30 seconds for the second question. Just a reminder, the second question is, how do you think you can measure the similarities of the data points and the classes? Actually, I'll give you guys a minute for this question because it's a little bit of a tricky question. So I'll give you guys a minute. Okay. Yeah, put your answers in the chat. What do you guys think? Sameness level, okay, that's nice. Do you mean RGB or RNG? What do you mean by RNG? Oh, random number? Random numbers? Okay, okay, okay. I see, I see. Define something quantitative. Okay, yeah, you guys are on the right track, right track. Anyone else? Any ideas? Okay. Yeah, so this idea of measuring something in a quantitative manner is a good idea. And I think you're on the right track there, as you know that since we're using a computer, we have to measure something quantitatively. So how are we going to do that? Well, the answer is we can actually use distance. So what you can say is that you kind of quantify um, how orange a subject is or how big a data like an image is, and then based on that you can graph it. So for example, if we were to treat these circles, if we were to treat these circles and these triangles as oranges and apples respectively, let's make the triangles as apples and let's make these circles as oranges, where the kind of the x-axis, this imaginary x-axis represents our color, and the imaginary y-axis represents, say, our size or the mass of the data, right? So as we go more to the right, we can see that maybe um, the object gets more red, right? The RGB value gets closer to red, pure red. And then as we go further up, maybe we can say from further up on our y-axis, we can probably say our size or our mass of our kind of image or in this case fruit would be actually less. So what we can actually do is we can use distance to kind of classify these these the data point, right? So the way this works is you can use kind of think about it as perfect circles, right? And here what we can say is that I'll say if we're trying to classify the star, right? The star in the center right here. What we can say is that I'm going to create a circle that encompasses only the first point, right? I'm only going to create a circle that encompasses the first point or the closest point. And the way I measure that closest point is by measuring the distance to all of the points. I'm going to create a circle that measures to the closest point. Then you can say, well, okay, that's only one data point. I want to have some more data. So I can create another circle um, that encompasses two data points or three data points, which is in our case, we have three data points. We have one yellow and then one yellow circle and two red triangles. And then you can say, okay, well, I think I still need more data. I still think that the radius of my circle, right, the closeness or how many data points it covers is just too close, right? So I need it to be a little bit bigger or a little bit smaller. So by doing this, you can kind of change the final radius of your circle, and by calculating the average mean distance between each of your points, you will be able to actually the average distance between each of your points within the set boundary or the set limit you have of your circle, you will be able to actually determine whether the star is closer to the red triangles or is it closer to the yellow circles. And you might be wondering, like, why are there different types of distances? Well, depending on the type of data you use, you can also use different types of distance. So this might sound a little bit confusing, but let me explain it real quickly. It'll make sense really fast. So you guys are probably most familiar with Euclidean distance, and this is given by, say, x squared plus y squared, the square root of x squared plus y squared, right? That's our formula for finding the hypotenuse or the shortest possible distance. Well, the Manhattan distance is something a little bit different. Imagine you have a grid, right? And in this grid, you're only allowed to take ups, downs, lefts, and rights. Well, the shortest distance from point A to point B if you can only take ups, downs, lefts, and rights, it's called the Manhattan distance, right? And the reason we call this the Manhattan distance is if you think about the city grids in like a big city or a big town like New York or Manhattan, they're made of these square grids where you can only go up a block, down a block, left a block, right a block. So you can't just like go across the block, right? You have to kind of, you can't go diagonally across the block. So you either have to go up, down, left, or right. So you can use this kind of idea of different distances to measure different types of data points and different types of kind of different types of information that you get. Does that make sense? Make sense, guys? Put a yes or no in chat. That'd be helpful. Make sense? Okay, that's good. That's good. We can go on. Okay, so as we talked about, we are always trying to find the kind of a k value that best suits us, right? We're trying to find that radius of the circle, which gives us the best kind of idea for where our point will be classified, and that's called our k, right? This is called our parameter, which is kind of the number of, you can think of it as this radius of the circle, but it's not specifically that. But for now, you can think of it as the radius of the circle. What radius do I need to best determine what the average distance is from the points within that circle, and then classify the point I'm trying to classify. So this idea of finding the right k, the right radius, is the hardest part in KNN optimization. And for this, actually, you, the data scientist or the machine learning engineer, are going to be going up, shifting the k and shifting this hyperparameter to make sure that you get it exactly as you want. So in order to do this, you can just obviously change it through code. But there is a really good rule of thumb for determining your k, and that is by taking the square root of the total number of data points. So for example, in this we have, let's see, we have five yellow dots, and we have five um, five red triangles, right? So the square root of 10, let's just round that down for a simple sake, is roughly equal to 3, right? If we take the floor of the square root of 10, or the lowest integer value of the square root of 10, we get 3, right? So that's why we can see probably our best k value would be 3. And you can think about this as our circle radius, or the approximate number of points that fall within a certain circle. So for us, that would be our second circle, because we have 3 points within our circle. So our best k would be 3, which would be our second circle, which we could then see is probably closer to the red triangles. We would classify our star as a red triangle, or I believe we called it an apple. The apples were the red triangles, and the oranges were the yellow circles. So we would classify it using our optimized k as a apple. I hope that makes sense. Okay. Now we can kind of get into the code. Yeah, we're pretty good on time, so we can now get onto the code. So right before we get onto the code, the first thing I want you guys to do is to I kind of want to see where your guys' Python skills are real quick. I know we kind of jumped into code last time really fast, and I didn't really get to test out where your guys' Python is. So we'll kind of just test out the waters in Python to make sure that you guys are kind of understanding how Python works and how to write basic Python. Okay, so I would say take around 2 minutes just to kind of go over this Python script and try to understand as much as you can, and then I'll go over it with everyone else. Okay, I'll give you guys 2 minutes to kind of read over the slide. There's no JavaScript in for what we're doing. This is Python. We can't see. Do you need me to zoom in, Toby? Okay. Is everyone done kind of reading the slide? Kind of going through it? Yeah, I'm gonna take that as a yes. So Toby and Daniel, if you guys would like to stay after class, maybe for 2 or 3 minutes, I'll answer your questions then. But we're kind of running a little bit short on time, so I'll answer your questions right after class. Okay. So yeah, as you can see, what we did here was it was just a print statement. So when we say print and we put quotation marks and we put some text, this will print something out to the console or our terminal. Oops, sorry. And then when we do something like a for loop, which kind of iterates, and when I say iterate, I mean it goes through something in X a number of times. So when I say for X in range 5, print X, you would print X 5 times. And in this case, X is not defined, but it could be defined as a string, which would just be some text. It could be defined as a number or as an integer or a decimal. So yeah. Then when we print nothing, we just get a new line in Python, like many other languages. The fancy, or not fancy, but the symbol, the kind of percentage sign you see in line 25 is actually the way that Python looks at modulus. And if you're not familiar with modulus, I would certainly suggest checking out our AMC and AMY classes. I think they cover that stuff. But and essentially, modulus is kind of finding the remainder of a number. So when you say if x, we read this as if x mod 2 equals 0. We're saying if the remainder of x when it's divided by 2 equals 0, we print x. Okay, and then a while loop is very similar to a for loop, but kind of different. And it's also this idea of looping. You keep on doing something until you meet a certain condition, in this case. So as the for loop, we kept on doing something for a set number of times. In this case, we're going to do something until we meet a condition. So until I is or basically while I is less than 4, or we could also say is until I is greater than 4 or equal to 4, we would continue printing I. And then each time we increase I by 1. So when we say I plus equals 1, we're increasing I by 1. Okay, so yeah, so I will send you guys the Google Colab link right now. Let me find it in my drive. Yeah, so okay. Okay, I have pasted the link in chat, so please tell me if you can see it or not. So if you can click on the link, that'd be great. And then, okay, again, like last time, please make a copy of it so you don't accidentally edit anything on the Google Colab itself. Please make a copy. Okay, let's get started. Let me get out of this. I'm gonna pause my share real quick. and I'll start it in a second, so we can go over the code. Okay. I think I can share my screen again. Sorry guys, my computer is buffering a little bit, so please bear with me. In the meantime, feel free to start reading on your own. There should be steps, so start reading on your own if you want to. Okay. Can you guys see my screen? Is it still loading for you guys? Yeah, my computer is being slow, so okay. Okay, so yeah, I guess we can go over it now. So the first thing, like always, what we're going to do is we're going to import our data and we're going to import our libraries, right? So remember, importing data and libraries should always be done first, if possible. This is just because it's easier for whoever's reading your code to do. So we'll be again using NumPy. If you want, you can just import as NumPy, but I recommend importing as NP because that's the standard. We'll be using pyplot, or matplotlib, pandas, and then we'll be using some things from sklearn. Sklearn is the same thing as scikit-learn, if you don't know. And then for the data we'll be using today, we'll be using data from Iris. And yeah. So again, the first thing we're going to do is we're going to run and import all of our libraries. We're going to do the cell by cell. Remember, Colab likes it when you run everything in chronological order. You start from the bottom, or you start from the top and you go to the bottom. So always remember that. Oh, are you guys not able to see my screen? Okay, it's good now? Okay. Good. Okay. So we're going to run the first cell to import our libraries. We're at that run, it's taking a little bit. Okay. So we ran our first cell. And the next cell, what we're going to do is we're going to import our data. So first, you can see we define a variable called URL as our URL path. Second, we assign certain column names to our data set. So in this case, we have sepal length, sepal width, petal length, petal width, and class. So we're actually classifying between flowers, if you don't know. I believe that's what Iris is. Let me double check. I believe it's flowers. Yeah, it's like an iris plant, and I believe that's like a type of flower. So, yeah. So we're going to run this section right here. So remember, the first part is we're just defining a variable with our URL for our data. Second part is the second line is we're kind of showing what our column names are. The third is we're kind of actually reading our data set into memory, or into this variable called data set. So if you want to see the actual head, or the kind of the first kind of tags and stuff, we can see it. So I'll go ahead and leave comments for you guys so you guys can see it. So we can see that these are what we get. We have a class of Iris setosa, petal width of 0.2, petal length of 1.4, sepal width of 3.5, and 5. I'm assuming these is in probably centimeters. Oh, Toby, did you have a raised hand by any chance? If you have a question, just put in chat. Try to get to it as fast as possible. Okay, so now that we're done with kind of importing our libraries and importing our data, what we'll now do is we will pre-process our data. Remember, this is probably the most important part of machine learning and kind of data science and artificial intelligence is that you always want to make sure that your data is clean, ready to go. There aren't really any big errors in it. So the first thing we're going to do is we're going to split our data set into our features and our labels, our attributes and our labels. So I'm going to go ahead and run that cell. And the next thing we're going to do is we're going to split our data into training and testing data. Remember, we talked about training and testing data early on. Training data is when we use data to train the model, and testing data is when we use data to test whether the model is accurate or not accurate. So we're going to run that, and our test size is 0.2. So what that means is that 20% of our data will be test data, and the other 80% of our data will be training data. The next thing we're going to do after we have split it into training and testing data is that we are going to normalize our data. And what normalizing our data does is that it makes sure that each and every feature can be uniformly evaluated and uniformly checked. So we tend to normalize our data just because of the fact that certain functions in machine learning and other models will work better when our data is normalized versus when it's not normalized. So there's a nice Wikipedia example that kind of explains why. So feel free to read that on your own time. But for now, we can just kind of make sure we ran everything and kind of go on to the next one. So I'll just explain what we're doing. The first one is the first line is scalar. So normalized doesn't really mean compressed. I guess you could probably call it compressed, but you're kind of bringing everything down to one scale. Generally, we try to bring everything down to between 0 and 1, but you're kind of transforming the data so it all becomes into one scale, so it's easier to read, especially for the computer. So kind of think about it as if you had something that was extremely big versus something that was really small. So if you had a data point that was of value 1, and you had a data point of the value 1,000 or 10,000 or a million, then the million would kind of skew up your data, right? So when you're normalizing, what you're kind of doing is you're kind of fixing that. It kind of is like dividing everything by the same number and kind of getting everything into the nice place. But if you have something really big, you might divide it by something a little bit bigger than what you're dividing everything else by. But yeah, generally, I think Daniel, you're on the right track for just dividing everything by the same number. To get data between a certain range. So the first part of the scalar equals standard scalar, we're just kind of getting initializing it, calling scalar, setting it to a certain calling the function and setting it to a variable. Then we're fitting our X train data, and then we do the same thing. We're transforming our data for X train and X test. So we'll just run that. Okay. Next thing we're going to do is we're going to train our model. So this is probably the easiest model you'll have to train due to the fact that most of the model can just be imported from the libraries. And this is from sklearn. So yeah. So here what we're going to do is we're going to just import our model, or not, we've already imported the model. We're going to initialize the model, we're going to fit the model, and then we're going to predict the classification. So remember last time we talked about prediction, but here we talked about prediction, classification, generation. In this case, prediction, or the predict classifier.predict, means it's classifying what it thinks the object is. It's not predicting a future value. It's not predicting a trend. It's not predicting anything. It's just telling you what it thinks the category is going to fall in. So don't fall for that trap. Just because it says .predict doesn't mean it's actually predicting a certain trend or a certain regression. Yeah, you don't have to be writing this code down. You can just make a copy of the Google Colab. I did put the link in chat, so you should just be able to kind of make a copy of the Google Colab. I think the way you make a copy is you can just go up. There should be something that says file, I believe. If you go like here, or maybe not here, or where is it? Yeah, there's a thing that says file, and then you can just do save a copy in Drive. I'd recommend doing that if you're using if you're using a Google Drive account or a Gmail account. Yeah, that's what I would do. How are you, Toby? Yeah. Okay. Now let's just train our model. We'll just run it. Here, we'll just run it real quick. Run the cell, and we can see that it has successfully ran. There are no errors, but that was pretty fast because this model isn't very intensive training. Yeah, so I would just say kind of just follow along with the coding right now, just so you have a general sense of what we're doing. But then later, if you're free, you can always edit it, kind of mess around with it. So again, here, classifiers, we can see that n neighbors is kind of our k size. So remember how I talked about it was either, you can think about it as k as the radius, or you can think about it as the number of points you're enveloping or circling. So we've set it to 5 in this case, but again, feel free to experiment, see what you get if you have a low k, a high k, something really absurd. What if it's above the number of points you have or below the number? I guess you can't really do below, this is be 0. Yeah. Okay. Now what we're going to do is we're going to evaluate our model. We haven't really covered this topic yet, but evaluating our model is kind of just seeing how well does our model perform, how well does it do. And what we can use is something called a confusion matrix. I know it sounds a little bit fancy, a little bit confusing, since it's called a confusion matrix, but don't really worry about it. It's just a way to measure the accuracy, the metrics, different types of things that the model is doing. So don't really worry about it, but what I would say, what I would pay more attention to is kind of paying attention to the classification report, how well it's kind of doing, right? So let's run this. So the matrix at the top you're seeing, this kind of weird double array looking thing. This is the confusion matrix. Don't really worry about it for now. Let's just worry about, you can even comment the first line out if you really want to. Let's just look at this kind of table here. So we can see that the position for the iris setosa is roughly a 1. For the vesicolor, it's a 0.92. For the Virginica, it's a 0.88. So it's not doing bad at all. It's pretty good. 0.93% accuracy for, I think, everything across the board, for the macro average as well as the weighted average. We haven't really talked about macro and weighted averages, but if you see a 0.9% accuracy, that's 0.93 out of 1, so it's a 93%. That's pretty good. I know for a lot of you guys, why is it called a confusion matrix? So the reason it's called a confusion matrix is because it's confusing. I believe that's exactly why it's called a confusion matrix, but don't quote me on that. I'm not particularly sure. But we can go over confusion matrix next time if you guys are really interested in that. Okay. Now what we can do is we can evaluate. So that's what we saw, right? We saw how did our model perform with a very specific value of k, or our n neighbors, where k was equal to 5, right? So the next thing we can now do is we can actually look at what happens if we have different k's, right? If we have different k's, what is the error? What happens to the error when we have different values of k? So this is a really small, nice script that I will show you and produce you a graph of how different values of k work. So for you can see here, again, we're creating a list called error, which you probably don't really need to worry about too much. But we're kind of calculating the error for values of k between 1 and 40, right? So we can see that by when we say for I in range 140, so for I in ranges 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, all the way to 40. That's what this for loop does. It'll do this thing for 40 different times, with I being in range of either 1 to 4, or 1, 2, 3, all the way to 40. So let's run this real quick. And now if we want to, it's already ran, it probably ran pretty well. Now if we want to kind of print out our values, we can run this plot figure, this kind of graph to show how it works. So we'll just run this graph, and we can see that we get a mean error, something that looks like this. So basically, until around 25, our mean error is 0.07. Okay, not too bad. And then our probably like 26, our error is really low, 0.03. Then it jumps to 0.1, and then it goes back to a little bit below 0.07, and then it kind of oscillates between 0.1 and that value before. So maybe our best k value is to do something like 0. Or 26k might be a really nice kind of k number. Okay, so that's it for today. You guys have any questions? Okay, so Daniel, you have a question. How does this underlying library function work exactly? So what do you mean by, because do you mean how the model works, or how you can import a library and then use the library functions? Okay, yeah, so the model is the same way as you can think it's the same model as our KNN model, right? It's the same. You look for the closest distance, and you take the weighted average based on the types of points there are. So remember, if you looked at our oranges and apples example with the circles and the triangles, we see that if you have a certain k or a certain radius of the circle, or the certain distance that you're going and looking for points, if the distance between the object you're trying to classify and say an apple is 3 and another, say, an orange is 4, then we can say it's closer to the apple. So then what we'll say is it probably belongs to the apple. So now if you're saying, like, what if there's multiple different types of apples, or if there's multiple apples and there's multiple oranges that are within our circle, then we take the distance from each one, and we can just take an average distance. Hopefully that makes sense. And again, you can take different types of distances. You can take your Euclidean distance, which is the shortest path, or you can take the Manhattan distance, which we kind of discussed about, which was if you have like a grid scenario, and you have to go block by block, what the distance would be then. And there's other types of distances, something called a Hamming distance, which you might learn if you're taking the Usico class. I don't know if they're going over Hamming distance, but it's part of strings. There's also something called a L1 norm distance, which is a pretty advanced topic, but it's basically instead of x squared plus y squared square root is the square root of x plus y. That's how you define another form of defining distance. So yeah, you guys are all free to go. Just answering questions now. So yeah, I'll probably stop my share right now. Any other questions from anyone? Okay, yeah. Well, please just remind me what your JavaScript question was, Toby. What was your JavaScript question again? It was something along the lines of, why didn't we go over JavaScript yet? Was that it? Yeah. So the reason we did, so I don't know where you're getting JavaScript from. Sorry. We haven't done any JavaScript in this class. And I don't think any of the other classes are teaching JavaScript. Yeah, we're not gonna teach JavaScript. This is not a web development class, so I hope that answered your question. And then I think Daniel, you had another question, right? Something about quadratic regression. Yeah, so quadratic regression would just be a regression, but in the form of a quadratic expression. So what that would mean is so usually the equation for a line is like fx is equal to mx plus b. So the equation for a quadratic function would be fx is equal to ax squared plus bx plus c. So you'd have a function of that form. So yeah, I think that answers your question as well, Daniel. Yeah, you wouldn't solve, but again, the computer would find values for A, B, and C by fitting the data. Okay. Okay, I think we're a minute over. So I should probably stop recording. Yeah. So bye guys. I'll see you guys later. Thanks for coming. Please come again. I hope to see you guys here next class. Okay. Bye guys. I'm gonna be ending the meeting right now.